Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera to everyone. So welcome to soil mechanics module number 2 under topic soil classifications part 1. Previously, we have been discussed on some simple tests that can be carried out without using a proper apparatus. I mean that simple testing without having a specific apparatus to classify the soil. Okay, but now we want to discuss two types of testing that need to be carried out in the laboratory for soil classification purpose. So we have we group into two. One is particle size analysis and another one is attribute limit test. Okay, for particle size analysis, we have two types of testing to be carried out at lab, which is Sieve analysis and also sedimentation analysis. On the other hand, for attribute limit test, you need to carry out two tests also, which is liquid limit and also plastic limit. Soil sample in natural condition normally has a various size, okay, of particle. Okay, so what are the definitions of particle size? Okay, when analyzing each grain, you will notice that not only they have a different sizes but also comes with different shapes. Okay, so size and also shapes are actually related to each other. Okay, different size of grain ranging from small, ranging from small to big. Okay, range from small to big particle, and different size grains subjected to different properties of soil. Those as geotechnical engineers, size of particles for each soil is very important prior deciding suitable foundation, especially for big structure. This table shows a range of particle size for different type of soil with different standards. Okay, with different standards. You will notice that there are slightly different in terms of sizes. In this topic, in most cases, the range of sizes for each type of soil will be discussed on the basis of British standard and also ASTM, but we normally follow British standard more compared to ASTM. So if you look at this table, you will see that different type of soil. Okay, we have gravel and sand. And what is a gravel and sand? It belongs to coarse grain soil group. And you also have silt and clay, which belongs to fine grain soil. Okay, and finer than that, what we call as a fines. So if you're talking about gravel, okay, for BS, the size range from 60 to 2 mm. Okay, we use the SI unit mm, and for ASTM, it's a little bit larger than that. Okay, for sand, it is less than 2. Okay, to 0.06 mm. Okay, so this is the limit. Okay, this is the limit of the grain size that normally we can see based on our naked eyes. Okay, lesser than that, okay, most likely we need to use a microscope. So for silt and clay, it has also its own range of sizes based on BS and also based on ASTM. In soil sample, we are interested to know how much of soil is the big particle and how much is the small particle presented. Although natural soils normally are mixed between various size particle, it is common to find a predominance occurring within a relatively narrow band sizes. Okay, we know that when talking about size of particle in even in small sample, you have a wide range of sample, especially for well-graded type of soil. So you have from big to small. Okay, but what we are looking for is we want to try to find the dominance. Okay, the dominance types of soil. So if you're talking about big to small, it means that it may have all type of soil. You have a gravel, you have sand, you have silt, you have clay. Okay, in the sample of your soil. But what we are looking for is which one is the dominance. Is it gravel? Is it sand? Is it silt or clay? It means that it consists the major percentage, okay, in that aspect, in that particular sample. So we want to know which one is the dominance. Okay, In classification of the soil sample, okay, there are two testing associated to particle size, okay, that need to be conducted. Okay, we have a sieve analysis, and we also have sedimentation analysis. Sedimentation analysis is also known as hydrometer test. Okay, hydrometer test. So this is the boundary. Okay, so this is the boundary. Okay, the boundary of the particle size in which that it can be identified based on sieve and also based on sedimentation analysis. Okay, if you look at here, the boundary is at 75 micrometer or 63 micrometer, approximately that value. So it's about 0.075 mm and 0.063 mm. Okay, so anything larger than that, okay, can be easily measured based on sieve analysis. Whatever that lesser than that can be measured by sedimentation analysis. And these two testing, okay, is measured, okay, a type of soil based on what? Based on particle size. Remember previous slide, to classify the soil, you have to conduct two set of testing. You have particle size and you also have ultimate limit. So if you're talking about particle size, you have sieve and you also have sedimentation. But those two, sieve and sedimentation, just classify the soil based on what? Based on particle size. Okay, let's discuss on sieve analysis. Okay, this method covers the quantitative determinations of the particle size distribution in a cohesionless soil. Okay, in a cohesionless soil. Okay, this may be a new term for you. What it means by cohesionless is actually similar to coarse grain soil. It's just that we use a different term. Later, I will explain why we use cohesionless term. Okay. Okay, we want to determine, okay, quantitatively the particle size distribution in cohesionless soil down to a fine sand size. And testing will be conducted based on the British Standard Procedures, okay, BS 1377, Part 2, 1990. The objective of the test is to group soil particles into different range of sizes and subsequently the relative proportions by dry weight of each size, which means that to conduct this test, okay, the sample must be dry prior testing, okay, prior testing, because we want to quantitatively obtain the percentage of each type of soil for range from cohesionless down to a very fine size, okay, in a dry weight proportions. This is the apparatus for sieve analysis. Okay, tests with the following aperture sizes or the equivalent standards may be used according to this size. Okay, so what you need to do is you need to arrange the sieve. Okay, the top one will be at the bottom followed by the small one. So the big apertures, okay, the sieve with the big apertures will be on the top followed by the small apertures, and finally we have the tray here. Okay, we have the tray here. Okay, here are the procedures to carry out sieve analysis tests. Okay, what you need to do is, okay, this is the first step. Okay, you need to weigh a dry sample, okay, to 0.1% of its total mass of about 200 grams. So your sample must be in dry, and this is at about 200 grams. Okay, it's about 200 grams. Don't be too accurate. Okay, it's about, okay. And then fit the largest size to sieve appropriate to the maximum size of the material, present to the receiver and place the sample on the sieve. Okay, and what you need to do before you shake, that you need to ensure that you have screw everything with the lids, and then you shake the sieve set using a suitable mechanical shaker for about 10 minutes. Okay, about 10 minutes, and then weight the amounts of retained material on each sieve to 0.1% of its total mass. So very simple test. Okay, very simple test. You take the sample in dry conditions, about 200 grams, put on the top of the sieve. Okay, remember you have to arrange first. Make sure the top aperture should be on the top, followed by the small aperture, and then make sure it's tightly screwed. Okay, press the shaker, shake the sample into within 10 minutes, and then you weigh the sample that retain means tertahan, retain on each sieve. Okay, this is the example of data recorded and calculated after carry out sieve analysis test. So to calculate mass passing, okay, mass passing is simply total up the mass of retain, okay, the mass of retain for each sieve, then minus with mass of retain for each sieve respectively. Okay, so I'll explain it one by one. Okay, the one that you record is actually these two. Okay, you have the lab sheet, you have the sieve size and mass retain. So you already this one is depends on your sieve. Some of you might not use this size, might use different size. Okay, it's okay. So whatever size that you use, okay, just record it here. Okay, record it here. And remember, in the end of the testing, okay, you weigh the mass retained on each sieve. Okay, let's say your soil sample total up is 200 gram. Okay, the 200 gram. So what you need to do is you need to weight, okay, on each sieve. Okay, so each sieve for sieve 10, let's say there is no particle retain on that. If there's no particle retain on sieve number 10, means that, okay, this is your sieve number 10, right? Sieve number 10, okay, it has its own aperture. Okay, we want to look at the particle that retains here. If you look at this example, the particle that retain on sieve number 10 is 0, which means that nothing here, everything passing through sieve number 10, right? So followed by sieve number 63 to until the final one, 63 micrometer. And you have to make sure that when you total up everything here, it must be at least, okay, the difference not more than 1%. So it means that total up, initially you put 200 gram, make sure you got 200 gram as well, or not, the difference not more than 1%, less than 1%. If let's say the difference is bigger than that, what you need to do is to retest it again. Okay, retested it again. So there's two. Okay, the mass passing and also mass passing, the percentage of passing is the one that you calculate, okay, from the data that has been recorded here. Okay, so how to calculate the mass passing? Okay, we know that the total, let's say after that the total is 200 gram, so that 200, okay, minus, okay, here because it has 200, because it has 200 is here, supposedly to 200 minus 0, it is 200. So 200 minus 15 equal to 185. 185 minus 36.7 here, and followed by the rest of that. So how to calculate the percentage passing? Okay, you look back, whatever that passing here, mass passing here, divide by total here, 200 times 100, you got 100. Okay, here 185 means that 185 divide by 200 times 100, you got 93, and followed by the rest. Okay, okay, once you finish everything, you already calculate everything. Okay, the data that you need for further analysis is only percentage passing and also sieve size. Okay, so moving here, you need to plot the data that you obtained just now, sieve size and also the one that you've been calculated, percentage passing, and analyze it, okay, with particle size distribution graph. So this is this graph, we call it as particle or grain size distribution diagram. Okay, so your y-axis is percentage passing and your x-axis is sieve analysis. Okay, remember last time, if you look at sieve number 10, percentage passing is 100%, so you have 100 here. Percentage at 6.3, below that, first 10 mm, and then if I'm not mistaken, 6.3 mm, about 93% if I'm not mistaken. So where's the 6.3? Okay, remember this is log size graph, log scale graph. So you need to rearrange the scale here. It's log 10. So for example, look at your size. Which one is the final? Just now is 0.063. So you start with 0.01 times 10, it becomes 0.1. You 10 times 10, it will be 1 here. Again, times 10, you got 10 here. Alright. So what you need to do, for example, like if you want to find size 6.3, so 6.3, where is 6.3? This is 2, 3, 4, 5, 6. Okay, so see here, 6.3 is maybe somewhere here, and for 6.3 size, about 63 particle passing, right? So here go down, it's 93, and followed with the rest. Okay, and another thing that you have to remember, if you look at this one, I connect each of point. Okay, this is the curve. It's curve, not straight line, but it is not necessary to connect each point. Okay, it is a best fit curve. Okay, so you can just plot like this. Okay, it's not necessary to. Okay, and the curve is somehow like S curve. All right. And the position of a curve that you get from the grain distribution diagram, okay, indicates the fineness or coarseness of the grains. Okay, the higher and the further to the left curve, the finer grains. Okay, so the higher the curve to the left, okay, near to origins, it means that it indicates that it is a fine particles, and the other way around. Okay, if it's the curve is higher to the right, it means that it is coarse. This is also depends if you arrange your size from small to big. If you reverse it, means that maybe this is big, from big to small, so it will become the other way around lah, right? And in the additions to that, the steepness or flatness and general shape also indicate the distribution of grain size for a given soil. Okay, for example, you can identify in terms of grading. Okay, remember when we mentioned about grading, we have well graded and uniform. Uniform also known as poorly graded. And you need to understand what is the what call that the definitions of well graded. Okay, well graded is covers a wide range of particle. Meanwhile, uniform graded, it covers only a certain range of size particle. So if you look at here, okay, for well graded, from big particle to small particle. If you're talking about uniform, it only covers a certain sizes only. In this case, it covers only on sandy size. So from that curve, okay, on your particle size distribution diagram, you can easily identify. Okay, and additionally, results of grading tests can also be tabulated using geometric properties of the grading curve. These properties are called grading characteristic. First of all, 3 points are located on the grading curve, namely you have D10, D30 and D60. What is that? For example, D10 means the maximum size of the smallest 10% of the sample. So what you need to do, okay, this is percentage of particle passing. You want to find D10, for example, you want to find D10, go to the 10%, okay, move to your curve and go down to the size here. This is your D10. And what is D10? Is the maximum size of the smallest 10% of your sample. The same thing for D30 and also D60. And from that, by using these two equations, CU, what is CU? Coefficients of uniformity, and CK, also known as CC, but we normally use CK, is coefficients of curvature. So using these equations, we will identify, okay, based on the equations, okay, either the soil is well graded or poorly graded. But as I mentioned previous slide, without having to calculate these two parameters, also you can easily identify from the curve. Okay, either it's well graded or poorly graded. But if you want to further proof, okay, with the values, then you have to provide these two values based on CU and also CK. Okay, with that, we stop for a while. I'll see you later on second part of this topic. Thank you very much.